The next problem, actually, I have broken it down into uh, parts. So if you see the actual problem, the problem is this one, this D that we are talking about. And what are these things? So suppose you have a finite set which will also be your input alphabet. So it has the symbols ABC, and you have a binary operator, say star, on this sigma. So that means they behave like some kind of algebraic structure, some sort of operation between them. So you can have some sort of table, for example. This 2.8b. Okay, so here some table is given, right? So this table means something like so you have this thing. So if you sort of do this, say A star B, you get A. If you do A star C, you get C. If you do, say, B star A, you get C. So this and this. So this table just gives you a tabulation for this some binary operator. Okay. So you have that. So instead of using a particular table, this works for any binary operator. But the important thing is that this is any binary operator, and this need not, this is of course not commutative, and this need not even be associative. So you say that this is not associative. So this operator is not associative. Okay, so it's not associative. And then we define two kind of products. Okay, so if you are given, say, a string where this A1 up to AN, they are symbols. So this is a non-empty string. See, this is in sigma plus. Sigma plus means the set of all non-empty strings. So you have a non-empty strings here, and these AIs are symbols. So they are either A or B or C. So we can define two type of products. One is like you first do this A1 with A2, then A3, then A4, then A5, then A6, and up to AN. Okay. Another, so this is doing the product from left side. So this L I wrote for this left side product. So another way to do this is from, say, right side. Okay, so you first multiply the last two symbols with that this symbol before that, then after you have this, multiply the symbol before that. So you are doing it from this direction, where you are doing this from this direction. So these two products will not be same in general, because this operator is not associative. Associative means that these products are same, right? But here these products will not be same. So the problem is to find all the strings such that if you do the product from left and if you do the product from right, then they should agree. So all those strings, so they constitute this language L. Okay, so you are supposed to construct a NFA for this language. Okay, So now I have broken it down into bits to make it easier for you to understand. So let us first construct this language. So here we are only concerned about this left side product. This is left type of product, and that has a particular value a. So you see here the value is what? If you multiply this is a binary operator, so the value is also from somewhere here, right? And if you are multiplying this, so the value is either a or b or c. So I'm taking those strings for which this left side product is a. Okay, so this I say L left a, and for this I design this DFA. So here I do not even need a NFA, so DFA will suffice. So what are the states? So I have this states QA, QB, QC, so they correspond to this A, B, C. Okay, so in fact I could have just called them ABC, but just to avoid confusion I use. So I have this QA, QB, QC, and I have one more state which I make a start state. So start state Q0. So I have some Q0 here. This is some other state. And final state is set of final state is QA. So I have only one final state, which is QA. So this one. Okay. So this is the final. So I have a double circle here. And this is the start state. So the first thing I do is from the start state I make transitions on A, B, C. So if I see a A, I make a transition here. Okay. Similarly, if I see a B, I make a transition here. If I see a C, I make a transition here. Okay. So this is the first transition. Now after this, all the transitions will be between this QA, QB and QC. I won't go back to this Q0 anymore. So that was used just to take the first symbol. Okay. So now how do I define the transitions between these states? See here the idea is so we can express this and this recursively. So in terms of some for example here so if this W is say A1 and then X, where X is from A2 to AN. Okay, so this X is A2 to AN. So then this means that f of L of W is what? F of L of X, and then this made a mistake. So this is not what I want here. So here I want XAN. So this X is A1 up to AN minus 1. Okay. So here I mean that this X is A1 up to AN minus 1. So and then we have this AN. So if this is the case, then the FL of this thing is if you take the product up to this n minus 1 and then take the product with say AN. So this is a recursive definition of this FL, right? And the base case will be this FL of any symbol. Say if this is some symbol, not string. So this will be this, because there is just one symbol, so just product is just this one. So similarly here, if I, so here I need to break it up like this. So here I need to break it up like a1 and then say x prime, where this x prime is a2 up to an. So then this fr of w will be a1 star fr of this x prime. Okay, so so here I'm just addressing this left side thing, and the idea is to always keep track of this thing. Okay, so this cumulative product sort of thing. So I want to set up my transitions such that this claim holds. Okay, so though I defined it like this and then made this claim, so when I'm solving this, so this should come before in my mind, and in order to satisfy this claim I set up my transitions. So you see that I have already set up this thing accordingly, right? So this means you have only seen symbol A and the product is A, so you are in QA, and here means you have only seen B and the product is B, so you are in QB. So already these things are showing the products where you have seen only one symbol, right? And now suppose you say that this is what you want, that you start from this start state Q0 and you see some string, and then whatever state you are in, the index of that state should give you the product, this left hand product, right? So the index of this state after processing W should give you this. So then this should follow, this should satisfy this thing, right? And this is what here we have here. Okay, so if you are in some state, say Q A prime, so and if you see some A, so then you move to this, because you should consider this A prime as this cumulative product so far, and then you are seeing another symbol, say sorry, this should be A double prime, this should be A double prime. Okay, so A double prime here. So yeah, so then you move to this thing, because you already have this thing and then you multiply this thing. So this A double prime acts as this AN, and this A prime acts as this FL of X, right? And again, it almost requires no proof, but the formal thing is to do an induction on this thing. So basis is length 1, because we are talking about strings of non-empty strings, right? So the basis starts with the length being 1. So that means this W is either these three symbols, A or B or C, and I argued that it already holds. And then again, simply, as I said, this W is some X and then say A double prime. And by induction hypothesis, what do we have? So induction hypothesis gives us that if you process this thing, so then the state should, the index of the state should hold the cumulative product for X, right? So this is by induction hypothesis. So then it simply follows that this is, by the definition of our delta, is just this thing, where this A prime is just this one. Okay, so A prime is up to X, and then we are doing this. So that's the proof for the left part. So the left part is easy, because you see the symbols and you just keep track of the cumulative product. So it's very natural. You should have figured it out immediately if you see this thing. So it shouldn't take more than few seconds to figure this out. Now the slightly confusing case is this. So is this right one, right? Because here the problem is you should start the product from this side. Okay. So I mean, it's there is no point in keeping a cumulative product for the first few symbols, because you see, suppose you have say some A1, A2 and then A3. Okay, and you are supposed to compute this, right? And also suppose you have some A1 prime and A2 prime, and then say A3. Okay, again you are supposed to do this. So you are seeing the symbols from this side, right? You are first given this A1, then A2. So even if you keep track of the product here, so even if you have say this, suppose you have this thing, and you have for a different input you compute this thing on some different run. Okay, so these two things can be same, right? It depends on your product table, as I showed. It is some table, right? And there, even though these two A1 A2 are not equal to this pair A1 prime A2 prime, so these two product can be same. They need not be same, but so that means this will not give you the information what these symbols are if you are just keeping the product. And then when you are doing this, these two may differ, because here you are doing this with A2 and then here with A2 prime, so these two may not be equal. So though they say are equal, they still cannot be can be different. So it won't help if you just keep track of so in fact it's not clear how to keep track of this cumulative thing from this right side. But even if you could do this for some up to say n-1, so then also it's not clear how to do this. So rather it appears that you have to do it from the other side. But how do you really do that, because you do not know what the future symbols are, right? So it's like knowing the future beforehand if you want to compute this, because you are seeing the symbols as A1 A2 A3. So that is why computing this part is far more challenging than the straightforward this FL. But you will see that okay, if we can do that with a NFA, we can also do that with DFA. And also there are straightforward ways to think about this using DFA, but that is slightly that is complicated. So we will see that with the power of NFA, so this non-determinism will really come to our rescue, and it will give us a nice way to tackle this thing, though we do not know what the future symbols are. So here is the solution. So here again I am trying to address a similar problem, but now I am saying that this is the right product is A. Okay, instead of left product, I am saying that this right product is A. A is some given symbol. Okay. A is some fixed symbol. So so here I have this thing. So anyway, it doesn't matter, I could have taken B or C. Now here I am using again this thing. So 3 states corresponding to this 3 symbols in the input alphabet, and again they are kind of keeping track of this cumulative product, and here I have PF. So in the previous case, that extra state was the start state. You see, this was a start state. So here I have a extra state, but this I will use as a final state. So again, our final state is just one, and that is this newly introduced state. So what is our start state? This is PA. And why I make this choice? Again, all this choice should come from some property that we should think of first. So this is the property. So somehow this state will have to tell you what that cumulative right product is, right? So this is how you do this. So now you see that suppose you are in this state, it's not the start state, right? So but this is some state, because this the B prime is some symbol in sigma. Suppose you are here, and then starting from here you are processing this string W, right? So now if you can reach this final state, so see, we are talking about NFA, right? So this delta hat, they are what? They are set of states, right? So this delta and delta hat, they are so what, this takes some state sigma and it gives you a set of state, right? So this hat again is some state then some string, and then this also gives you a set of state, so 2 to the cube, right? So that is why we use this thing. It's not equal to PF. So we said that starting from here you can reach this final state processing W, if and only if this cumulative sum is this B prime. Okay, so this kind of looks magical in the sense that you haven't seen this things yet. Okay, the symbols here yet, you haven't seen it, but somehow you are already in this PB prime, such that your cumulative sum will be B prime, right? So this this looks quite amazing, but we can satisfy this claim by carefully choosing our delta, and that happens because we are using this non-determinism. So let's talk about this delta and the proof. So you understood this part, I presume. So this says that this should not be the start state, this PA. Suppose you are in any state P, B, and if there is a path to the final state that we introduced, this PF on W, so this happens if and only if the cumulative sum for this, the right type, this is right cumulative product for this thing is B prime. So it kind of already knows what's going to be the thing. So now if this claim is true, before proving this thing, if this claim is true, okay, so we are trying to capture all the strings where this product is A, right? So that is why our start state is what? PA. Because from PA, if you can reach PF, so that means the cumulative product is So here it's a whole product, that is A. So that is why we chose this thing as PA, right? Then what about this thing? So as I said, this PF is final state. So we have again this picture. So PA, so we have PA, PB and PC. Okay. So as I said, if you are in PA and if you have some string which takes you to PF, so then that will be the right product, right? So this means what? What is the string here? So this transition is on A, right? So you see this from PA you have this transition. Okay. So this I should put, since this is a NFA, strictly speaking I should put this thing, but this is a singleton set, so I should put this thing here. I should put this here. So yeah, this is a singleton set. So yeah, so here this W is just A. Here if you start from here, the W is just B. So that means the product is A or B or C, because you are only talking about one symbol as your string, and then this property is satisfied for this length 1. So we are already we already have this basis for the induction for proving this, and that is why we set this up, right? So you see how we first think of something like this, and then this dictates us to define this thing. So it's not the other way around, that you somehow first construct this thing and then try to see whether this claim is. So this is how you write, but when you are solving the problem in your mind, it goes the other way around. So anyway, we have this transition from here, we have transition on B, from here we have transition on C. So, and then like before, the other transitions are between these three states. So there is no transition from here to back here. No, all the transitions are from here to here. So once you reach here, there is no going back. So all the other transitions are between these states, PA, PB, PC. And what are those transitions? So this is our transition. So this is important. So you take any two symbol in your input alphabet, and then you put a transition like this. So from P A prime star A double prime, on input symbol A prime, you are going to P A double prime. Okay. So we are putting this here. So you remember, this is a set. There can be many transitions. So what is it saying? So it is saying that in the transition diagram, it is saying that we are putting an edge, say P A prime star A double prime to P A double prime, okay, on symbol A prime. Okay. So this is what the HBR, and why is it a NFA? Okay, why is it an NFA? Because you see, so this binary operator is some binary operator. I mean, it's not associative, not cube. So that means this thing. So this is some B prime, right? So this this A prime star a double prime here. So this is some b prime, say, okay. But then the multiplication can be such that say it is also some a prime into, say, c prime. So suppose this is also b prime, right? So this is a transition between some p b prime to some p a double prime. So this state doesn't give you a breakup of this thing, right? So that means from this b prime, so from this pb prime, you have on, say, a prime transition to p, say, a double prime, and for this you also have a transition on this input, the same input symbol, to, say, this pc prime, okay, for this. So you see that you automatically get NFA. So you can have transition to multiple things on the same input symbol. So for this, okay. But these are all the transitions that we are going to put. For all, we go for all pairs of symbols, and then we put just this transitions between this. Apart from this, we have just this 3 which we defined here. Okay. So once we do this, you see that again it's completely motivated by this property. Okay. So this kind of is a case where it guesses. So a non-determinism is like making sort of guess. There can be multiple possibilities, and to take one possibility. So when you are in some say pb prime, okay, you do not know what the next symbol is going to be or whatever, but you but here you can make sort of guess for this thing, because this is whatever this is either A or B or C, right? So you can make some guess what this is going to be, and for this guess you can have multiple actions to take, and that is what motivates this thing. And once you set this up, it's fairly straightforward to prove the induction. So as I said, it's proved for the basis, and then what do we have? As we said, in this case, the recursive way of breaking this down. So this will be here. So here in the first we have taken one symbol and then the rest of the string. Okay. So by induction hypothesis, then what do we have? So first say that okay, we are trying to prove that this happens if and only if this happens, and so we are trying to prove it for this W. But what does this means? If we break this W into, say, A prime and then X, what does this mean? So then it means that you are taking a single step transition from this say PB prime. So you are making this transition. So then you can go to multiple state, but there is some state between the possibilities that is given here. So there is some state called that PA double prime, such that from this state, if you process this X, then you can reach this PF, right? So this is what this means. This means that starting from PB prime, processing this W, you can you can reach this PF. So this statement can be broken down into according to this breakup, that you first process this A prime, then you reach some state, and from that state you can process this X, and then you can reach this PF, right? Now we will break this part and this part. So this X has shorter length than this. So since we are doing induction on the length, by induction hypothesis, this tells us, so this thing by induction hypothesis, this part tells me that this A double prime is actually the cumulative product for this X part. Okay. So this is what our claim is. So this happens for this X part, right? So if this is the case, so by this thing, that this thing is this multiplied by this, so this thing is this into this, because this part is just this for X, right? And the first symbol is this thing. So we have this. And then this is, so what does this means? What does this means? Now this is where our construction helps. So this happens if and only if this B prime is of this form, right? You see, we put this thing into some state and this some symbol if this thing is the product of this and this. Okay. So that means this happens if this B prime is the product of this thing and this thing. Okay. So what is this thing is then? So it's this thing which is this thing. So this thing is actually this thing. So this is what we were trying to prove, right? This is the statement we were trying to prove. So you see that we can actually compute this product for this right product also. It is quite an amazing application of this non-deterministic automata. So in fact, while solving problems, you should try it first yourself, and that way you will appreciate where the difficulty lies. Or you may come up with some other clever solution, more elegant solution of your own. That happens all the time. Students come up with their own very nice or clever solutions. But even if you cannot solve this, at least you will appreciate where the problem lies. Okay. So now we have tackled this left product and right product. So now how to put these two things together, because you remember we are finally trying to construct this language where these two products match. Now before doing this, again previous step where we say that they match, but this answer is this particular A. So in general this answer can be A or B or C. but here we fix that this is A, and for that we construct an automata. So we have constructed this ML and MR with this parameters, this QL and this delta L, and this for this right we have this QR and sorry, I should have a delta R here. I should have a delta R here. Okay, so we have that. So now we are taking pairs of those states as a state in this automata. Okay, the idea is that this automata will simultaneously capture the run of these two automatas MR and ML. So here the state are pair of states, right? So a pair of states is mapped to a pair of states on some symbol, right? So this symbol makes this transition from this pair of state to this pair of state, and these pairs are nothing but this. So if in say ML we have this transition on this symbol C prime, and if in MR we have this transition on the same symbol CR. So these two transitions are just sandwiched here. So it's just almost a notational trick to cram these two things into this one thing, this one product. So this is actually a transition between these things, a pair of state to pair of state. But yeah, we put a edge here if we have the corresponding edges from here to here and here to here. So this is running everything together. And what will be the start state? So the start state is again, so the start state for this ML and MR, right? So this was the start state for MR. This is ML. This was the start state for MR. So their pair is the start state here. And what is the final state? So in this MR, so the final state was this, and in this ML this was the final state, and in MR this was the final state. Again, though that was a NFA, and so we had unique final states. So this will be the final states because this is where we want to reach. So the L part should reach here, the R part should reach here. So with this trick we sort of run this two automata together, and this works for this symbol, right? Because this is hardwired into this part. Okay. Now what is this thing? This is just union of LA, LB and LC, right? So if you see, L is just union of LA, LB and LC. So these are just special cases where they match, but the value is A, they match, the value is B. So the value is either A or B or C. So this is just union of this thing. And in the regular expression video, where we also proved that regular languages are closed under union, and we gave explicit construction, NFA construction to construct automata for those unions. So this was the construction. So if you have union of many things, so you just make this epsilon transition, go through this, and then make this epsilon transition. So that was the construction we used there. So we gave all the argument there. So this will be the construction for this union. So finally we answered this question. Okay. So finally I want to address one problem which is kind of related to a problem I gave you in quiz. So now these are regular expressions which are given. So this R and S are, say, given regular expressions, and this is a equation. So this X is unknown. Okay, this is some language which is unknown, but it satisfies this equation. So the question is, what is X? Now, first of all, is there any solution? If there is any solution, is that solution unique? If it is unique, what is that solution? If it is not unique, then what are all the solutions? So all these questions are there. So now we will see that there are two cases, distinct cases. One is that this. So first of all, we are using regular expression RS. So strictly speaking, in order to address the language denoted by this thing, we should have used this LR. But just to make this clutter free, I'm using this R interchangeably with this language. So I'll use this sort of notation. You see that I'm treating this as a set. I'm treating this as a set rather than just regular expression. So interchangeably, I will use them as regular expression and the language that is denoted by this. So the first case is that this R, this does not contain this empty string. Okay, this is the equation that we are trying to solve. And okay, so then our claim is that there is a unique solution. So unique solution. And that solution is X equal to R star S. Okay. And how to prove this? So in order to prove this, first we prove that this is a subset of this, and then we prove that this is a subset of this for some I. Okay. So let's first prove this. So we do induction on I, obviously. So if I is 0, then this is just up to the 0, which is just singleton set consisting of epsilon. So this is just S, and S is part of this because this is union of this and this. So obviously this is a part of this, and this is X. So this R0S is in X. So now if this R minus 1 S is in X, we can take concatenation in the left side by R. So this is in this XR, but XR is part of this because this is XR union something else, right? And this is X. So that means this is a subset of this. So this is done. So this is done. Now, in order to prove this, we show that. Oh, sorry. This is. I wrote. So I should have written this way. And just. So I should have written this way. To the I, yes, yeah, this is what I want. So this way and this way. Okay, and in order to do this, I will prove this, that if something belongs to X, then that thing also belongs to this RIS for some I. Okay, this I and this I are not equal, so for some I, so that is why we have to consider this R star S, because union of all I. Okay, so basis. So basis is again. So we are doing a induction on length of W. So basis is length 0. So this is epsilon. So sorry, this is again, this is R, this is R. So epsilon is not part of R. Okay, so this is our this is the case that we are considering. So epsilon is not part of R, so that means epsilon is not part of Rx, right? Because we are concatenating strings from R and X. So if all the strings here are non-empty, so then if we concatenate it with some other strings, so all the strings here will be non-empty also, right? So this holds. So this means since this epsilon cannot be here, if this epsilon is in X, so this means that this epsilon must be either here or here, but we have proved that this cannot be here, so this must be here. And this S is R0S, so for some I, so this I here is 0. So the base case is done. Now we do induction for length more than 0. So if this is in X, what is X? X is this union this. So that means this W should be either in S or in this Rx. Now if it is in S, S is R0S, so that means I can pick I to be 0. So this case is done, or there is another possibility that this belongs here, right? But if it belongs here, that means it's concatenation of two strings, W1, W2, where this W1 is coming from this R and this W2 is coming from this X. So W1 is coming from R and W2 is coming from X, because this is concatenation of this and this. Okay. Now you see that this W1 cannot be empty, right? Because it belongs to R and R does not contain epsilon. So this W1 cannot be empty. If this W1 is not empty, so then this W2 is shorter than W. Okay, because you have taken some symbols here, so this W2 is shorter than this. And if this is strictly shorter than this W, then we can employ our induction hypothesis, right? Since we are doing induction for W2, it holds that this W2 is member of some Ri to the S. Okay. That is what we are trying to prove. So for some I, so then what is W? W is W1, W2. W2 is coming from RIS, and W1 is coming from R. So their concatenation is coming from R to the I plus 1 S. So this is also here. So for some I, okay. So this I you should not confuse with whether it's I or I plus 1. I'm saying that this is sorry, this should be star. This should be star. This should be star. This should not be I. I mean, what I mean is this. So this is contained in R star S, means if a string is in X, so then that string should be in some R to the I S. So this should be this should be the right expression. You should not put a particular I here. Okay. So yeah, this statement is equivalent to this statement. So this is what we are proving for some I. Okay, so this is the case for R not containing epsilon. Now what if it contains epsilon? Okay. Now if it contains epsilon, you just choose this R prime which such that you remove this epsilon from R, and then you get, say, this R prime. Okay. So then R prime does not contain epsilon. Okay. We have explicitly removed this epsilon from R. And also you define this thing. So this you take all the strings in X which are not part of this. Okay. If there is any, this can be empty also, this can be non-empty, but whatever, this is some set. Okay. So now you see this equation implies this equation, right? So this x prime is what we get after taking this out from this set. So this set is what? This union this, and this plus is union, right? So this thing will be this thing union this thing union this thing. So I have taken these two unions together and this outside. Okay. Now you see this looks exactly like this case 1, right? So this r is replaced by r prime, where r prime does not contain this epsilon. So this is exactly same as case 1, and then we have something instead of s, we have some x prime plus s. So what was the solution, the unique solution for this case 1? So it's star of this thing followed by this thing. So this is the solution, right? And this solution is equal to this solution. So you may say that there's a typo, that I missed this this is primes here, but it's not the case. See, r prime is just r minus this thing, and if this is the case, you can take this as an exercise that r prime clean star, so this will be actually r star. Okay, so you can take this as an exercise to prove this thing. So this happens if r is equal to, say, this. So we can have this r star here, and this thing distributes over this thing. So we have this. So you see that earlier the solution was just r star s. Now we have this extra part, right? Now what is this thing? We do not know. I'm kind of defined it using like this. But see, we can take anything here. Okay. We can take any set here, and accordingly we will get some solution, right? So we can, if we make this this empty, so then the solution we get is r star s, but we can take any non-empty set here also. So there is no unique solution. You get infinitely many solutions for infinitely many choices of x prime, but all the solutions are of this form. Okay? It must be of this form, that r star s union r star some other set. Okay. So one example is, say, take r to be this. This contains epsilon. See, this contains epsilon, and this is just b. So these are regular expressions. So as a set, that means this is the set epsilon and this a, and as a set, this thing is just the singleton set b, and then you can check that this will be a solution here, right? So we have introduced another symbol c. So this is a solution here, because what is it? So if you take rx, what do you get? So rx will be say, first you say multiply with this. So a plus b, plus means non-zero number of ones, so this star means 0 or more number of ones, union a plus c, but then this epsilon is also here. So if you are taking this rx, then you also have x itself, right? So then you also have a star b and a star c, but this a plus b and a plus c are already contained in a star b and a star c, so this you can remove, they are already consumed here. And then you have s, which is just b, but then this b is also taken care here, because here you can put 0 number of a's and then this will be b. So this b separately is not required here. So you see that rx plus S is also this thing which is our X. So this is a solution. But how did we get this solution? We just picked this X prime to be this C, some other set. So again, this is just a singleton set here. I mean, you can take arbitrarily complex sets here, but this will be the solution. So yeah, until this R is epsilon free, you do not have that unique solution. Okay.